Okay, as you see in this section, 10.5, we're talking about tangents. Now, you've seen the word tangent before with sine, cosine, tangent, but this tangent really has nothing to do with the sine, cosine, and tangent. Uh-oh, announcements. Let me pause. As you can hear, I'm in school. This is right after school trying to get this done. So let's do this. Let's talk about circles, because you say, oh, I thought this was about tangents, but we talk about a tangent in reference to a circle. So let's put a circle up here, and then we'll talk about what the tangent is. So there's a circle. A tangent's actually a straight line, okay? Well, straight line, that's redundant, but it's a line, and here's a line right here. Now, this is not tangent to the circle yet. It's tangent to the circle when the line hits the circle at one point right there. So it's one particular spot. So let's say it hits the circle right here, and you're like, well, it kind of looks like it blends in here and here. But remember, a circle doesn't have any width to it, and same thing with a line. So actually, there is a place. There's one place where the line can hit the circle, and we'll call that place right here. So this line, you could even make it a line segment, but technically a tangent is a line. It keeps going in both directions. So this thing right here is the tangent, and the point even has a name. See where the point where the tangent hits the circle? This point, lo and behold, is called the point of tangency. Not that hard to figure out. The point of tangency. That's the point where the line hits the circle. So that would be the point of tangency. You could put a point here. You can name the line. They do a couple things in the book, but I think that's pretty good. They do this other thing called the common tangent. It's really not all that important as far as the homework's going to be concerned, but we'll take a look at that very quickly here. Okay, here's two circles right here, yellow one and a blue one, and I'm going to talk about a thing called the point. Oops, sorry, a little mistake. We're going to call this the common tangent. So what is a common tangent? This is one situation where you can have a common tangent. There's a couple different situations, but this would be a common tangent would mean a tangent that's in common with two separate circles. Now, if this circle right here was over here, you could still have a common tangent, but it's going to look a little different. So let's just stick with this circle right here. So how would I draw a common tangent? It's a tangent that's common to both of these. So this would be a, let's see, make sure I'm doing this right. Yep, a common tangent. So I might have to scooch it over just a little bit. And let's make it a different color than the blue. Just make it white. There we go. All right, so this line right here, this is a tangent to the yellow circle because it hits the yellow circle at one point, and it's tangent to the blue circle because it hits the blue circle at one point. So this is one example of a common tangent because it's a tangent that's tangent, or it's a line, sorry, that's tangent to both circles at the same time. Okay, both circles it's tangent to. Let's look at another example of a common tangent. Okay, here's those two same circles, the yellow one and the blue one, but I separated them a little bit, and let's see if we can find a common tangent there. So there's actually several different ways that I can draw a common tangent. I can draw one. I might have to mess around with this a little bit. Might not be exactly right. I'll tell you what I might have to do is move the circle just a little bit. Actually, let me think. I could probably rotate just a little bit like this and down. Might not be exactly right, but you get the general idea, I think. There we go. All right, that's pretty good. Look at this. This white, this is a tangent, okay? I don't have to keep putting arrows on there, but you get the idea. It keeps on going. It's tangent to the yellow circle, and that same tangent line, we'll call it L for line L, is also, it doesn't quite look like it hits right here, but we'll pretend it does. Okay, it's also tangent to the blue one. So if it's tangent to both of them, that's considered a common tangent. Well, let's see if I can draw any other common tangents. Do you see any other ones? Yeah, down here like this. This would be a common tangent as well. And so it's tangent here, it's tangent here. It's tangent to both of them, so I can call it a common tangent. You got some other common tangents. This one might be a little trickier to draw. So watch this. I can go like this, and I could rotate this just a little bit like that, and then I'll have to rotate this one. It takes a little bit of doing with this program, but that's close, man. We're close. Let's see. Let's click on on that. Sorry, taking all this time. There you go. That's good enough for us. And it's tangent to the yellow one, and it's also tangent to the blue one. So look, it goes through the two like this. That's also a common tangent. So when you have two circles that are separated like this, you get 1, 2, 3. Are there any more? I think you see it, don't you? Let's see if I can come close to drawing it. Might have to just play around with it just a little bit. Like that. Maybe a little bit more. Like that, and then let's try moving this one up just a little bit. Looks like it would be easy. It's not quite as easy as I thought. So watch. It's tangent here. It's tangent here. So look, I got 4 of them. Call this L, N, and we'll call it P instead of O. Looks like a 0. All right, so I've got 1, 2, 3, 4 different tangents to these 2 circles. So those are common tangents. They'll ask you a question or two about them. I probably spent twice as long as I really needed to on it. Let's go to our first theorem of this section. Now this theorem is pretty useful. This is a circle, obviously, with a tangent drawn, and there's the point of tangency right here. I'll put a little point right there at the point of tangency. Now watch what happens. If I draw a radius, that means I have to go from the center, and I draw it to the point of tangency. Sorry about that. There we go. If I draw it to the point of tangency, and if I draw it right there, look where it ends up being. Scooch it just a little bit. Look at this. This is the radius. Okay, that's the radius of the circle, and it's drawn to the point of tangency. I'll just write it like this. I've never really seen it like that before, but we'll do that. We'll call it that. The point of tangency. So it's drawn right here. What do you think might be true about the radius? And this is the tangent. Let's write tangent right here. Okay, so what do you think might be true about this radius and the tangent? In fact, tell you what, let's try a little trickery here. And let's see if I can do this. I think I might be able to. Okay, watch this. It doesn't have to be just straight down and straight across like this. Look, it doesn't matter. If I could bring it up here like that, this is still tangent to the circle, and look at the angle that's formed right here. I want you to see that it really doesn't matter where on the circle, right, you draw that. It's off a little bit right here. Sorry about that. I don't know why it's off there, but maybe I didn't draw that tangent perfect. And we'll just put it back to where we started. That's close enough. All right, if you noticed, it stayed a 90-degree angle all the way around. So if I draw a radius to the point of tangency, I'm always going to get a right angle. Now this is a right angle to the tangent, not to the circle, because the circle's curved. You can't have a right angle to a curved surface like that. So the radius is perpendicular to the tangent. So that's pretty interesting. At the point of tangency. So right here, right where that point is, it's going to be perpendicular to the radius. And that's a theorem. It says in a plane, a line is tangent to a circle if and only if it's perpendicular to a radius drawn to the point of tangency. That's theorem 1010 at the top of 719, page 719. You'll see that theorem. Okay? You're like, okay, well, big deal. So it's perpendicular. So it's a right angle. Well, what's the first thing you think of when you think of right angles? I think of Pythagorean theorem. Oh, they're going to make an announcement and they fake me out. All right, so, but I don't have a triangle here, do I? Well, let's take a look at this next example and let's see how we can use this thing. Okay, here's the example. What we have is a circle with a radius drawn, okay, from J to L, that's the radius. And what we want to do is we want to determine whether or not that KL is actually tangent to circle J. I want to find out is KL actually a tangent. Well, how do we know if it's a tangent? Well, we know if it's a tangent if this is a right angle. And how do I know if that's a right angle? I know this is a right angle if this triangle, if the Pythagorean theorem works on this triangle, then I know that has to be a right angle because I know this has to be a right triangle. So let's give it a shot. Let's see if the Pythagorean theorem actually works on this and makes this, it actually works on this triangle, okay? Because if it didn't, it wouldn't be a right triangle. So let's see. What is Pythagorean theorem? It's a squared plus b squared equals c squared. C is the hypotenuse, and a and b are the legs. So what are the two legs of this triangle? Well, one leg is 8. So we'll square it, and the other leg is 15, and we'll square it. But if you look at this, look where they put the 9. They put the 9 right here, and they put it there for a reason, because 9 is the distance from here to the circle. It's not the whole entire thing. They'd probably put they would do like that if they wanted to tell you the whole entire thing. They just tell you the little bit right here, which is 9. So how in the world can I tell what kj is equal to? Well, remember what the radius was. The radius was from the center all the way to a point on the circle. Well, they don't put a letter here, but from J to this point on the circle, how far is that? Well, that has to be 8. Do you see that? That's a radius, and that's a radius from here to here. So now we can do this. We can put a little bracket or brace right there and figure out what the whole hypotenuse is. It's just 9 plus 8, so the whole thing is 17. So I want to see, does this thing work? Is 8 squared plus 15 squared equal to 17 squared? Well, this is 64. This is, I think it's 225. And 17 squared, I believe, is 289. All right, and let's see if that works. Well, 64 and 225, there's a 9, and there's a, I'm sorry, the 6 and the 2, that's an 8, and there's a 2. So that's 289, and look at that. 289 equals 289, and yes, that must be a right triangle. Okay, if a squared plus b squared equals c squared, it must be a right triangle, which means this has to be a right angle. If it's a right angle, what does that mean? It means that KL is tangent to circle J. Okay, this is kind of the same problem, but just a little bit different. They actually ask you to solve for something. They don't say verify that it's tangent or anything like that. They actually tell you to solve for x. So how will we solve for x? First of all, they got to tell you something. Okay, they have to tell you that JH is the tangent to circle G. And let me see the example here. Looking at the right one. Yes, they do that. They tell you that JH is tangent. So if it's tangent, look where it hits. It hits the point of tangency is where the radius hits, right there. So what does that tell you? That tells you that you must have a right triangle. So that's very important. They tell you that JH is the tangent, and if it's tangent to the circle right here where the radius hits it, see where they come together right there? That must be a right angle. That's what this whole lesson's been about. And what do? We got to solve for x. How in the world do I solve for x? Well, it's a right triangle, Pythagorean theorem again. So let's see. It's going to be x squared plus 12 squared equals, don't be too quick to put 8 squared. You got to remember, 8 is from here to here. That's where the 8 is, from there to there. We want to find the whole hypotenuse. So what in the world's the whole hypotenuse? Well, if I knew what it was from G to the circle, then I could probably figure this out. So what is it from G to here? Well, that's a radius too, isn't it? Look, that's a radius. What was the radius of the circle? It's x. Now in the book they actually put the x there. I left it out so you could think about it for a second. So now what is the whole entire hypotenuse right here? It's not 8x. A lot of people say that. They say it's 8x. No. If I was going to figure out what this length is and what this length is, how do I find the whole thing? I'd add them together. So this is going to be x plus 8. So it's going to be x plus 8. Now we have to square that in Pythagorean theorem. Make sure you put that in parentheses and square it. Now the math we're going to do here is a little bit beyond what we normally do in geometry, but it's definitely something that's taught in a lot of Algebra 1 classes. So I'm going to go through it kind of quick. You might want to look it up at some point on the algebra part, but this might help you out. So x squared plus 12 squared equals. Now how do I square this? When I square a sum like this, make sure you multiply it by itself. You can't just go x squared plus 8 squared. There's no distributive property with exponents. So you have to multiply it by itself. And once you multiply it, I'm going to do the math kind of quick here. So it's going to be x squared plus 8x, which is plus 16x, and then plus 64. Okay? That's FOIL method, by the way. Should have mentioned that. I'm just going to change the 12 squared into 144. So what are we going to do here? Actually, the math is pretty easy on this. It's not that hard. The only thing kind of like stuff we haven't really done much is that FOIL thing. But that should be easy. Look what happens here. I can subtract an x squared from both sides. X squared, I should put. Okay, look what happens. They cancel. So the x squareds go away, and that's really nice. Let's do this. Let's take the 64 and subtract it from both sides. So I'll take the 64 and subtract it from here, and I get 80 right here, and I get 16x here. Divide both sides by 16, and x is 5. That's all they ask you for. Okay, they don't ask you to plug anything in. All right, x is 5. That's it. Now, what would this be? Well, it's just be 5 plus 8. What's 5 plus 8? It's 13. I don't know if you remember, but in the right triangle chapter that we had done, this was one of our special triangles, Pythagorean triple, 5, 12, 13. So that could be very useful as well. But you still had to figure out this was 5, all right? And that's how we do it. All right, let's see what else we have. Okay, I'm starting off with the circle right here. Watch what I'm going to do. I'm going to put a point outside the circle, okay? So just put a point out here so it's not on the circle, just away from it. I don't want it super close. It's kind of hard to do this if it's really, really close. So I put it away a little bit. So what I'm going to do is I'm going to draw a line, not just any line, but I want to draw a line that's tangent to this circle from this point. So I start at this outside point, start here, then I'm going to draw a tangent. Remember, it's got to come down and hit, boom, right there. That's where it hits. Now, just to clean this up a little bit, I'm going to draw in the point of tangency here. I kind of got a little bit hanging over here, and that's perfectly fine. But for what we're going to do, I'm going to take this, and I'm going to take it right to the point of tangency. So it's still tangent. Still only hits the circle at one point. Okay, because if it kept on going, it would get off the circle again. It only hits here. If it kept on going, it'd still be tangent. I want to do the same thing to the bottom of the circle. So I've got one tangent right here, and from that same point on the outside, I want to start here, and I want to draw it tangent to the circle here. There we go. Draw the point of tangency, which would be here. Just clean it up a little bit. Move this line in to where that point of tangency is, and I'm good to go. So here's our situation. Our situation is I have two tangents drawn from a point outside the circle. And we have a theorem that says if two segments from the same exterior point are tangent to a circle, they are congruent. So let's put some letters in here. If I call this A, call this B, and call this C. If AB was tangent to this circle, we'll call the circle Z. All right. So if AB, line segment AB, is tangent to circle Z, and if AC was tangent to circle Z, then these two segments from A to B to the point of tangency. Now you kind of understand why I took that tangent and I took it down to here. All right. Those two segments from A to B and from A to C are going to be congruent. So that equals that. So I could say that line segment AB is equal to line segment AC. When does that happen? When you have a point outside a circle, it's tangent to the circle. Both of those tangents are tangent to the circle. Then those two segments from A to the point of tangency and from A to this point of tangency, they must be congruent to each other. Let's do an example and we will be finished. All right, this is a super easy example as long as you know what the relationships are. What do we have here? This is a tangent. And they tell you, okay, in the problem, I didn't write it down up here, but they tell you that BA is tangent to circle D and BC is tangent to circle D. So if you know they're both tangents and they're both tangents to the same exterior point, the same point on the outside of the circle, that means these two segments are equal to each other. And that's all you got to do. Set them equal to each other. You've been doing this hundreds of times in geometry. Subtract x, add a 5, and that's what that is. If they ask you to solve for the length, and I don't think they do on this, they say find x, but they could say find the length of AB. That wouldn't be hard. You take the 20, you put it in for here, you plug it in, so it's 20 plus 15, and that would give you 35. So it just depends on what they ask you to do. They could ask you either way. Well, BC would be the same thing, wouldn't it? Put a 20 in there. 2 times 20 is 40. Minus 5 is 35. You can see that they are equal. Well, that's it. Look at that. Another one under 20 minutes. I'm doing great. I'm trying to keep it as low amount of time as I can. Good luck with this lesson, and we'll see you in class.